Hello everyone, I am Darshan A, Assistant Professor of Mathematics. In the previous sessions, we have learnt about differentiability. In this session, we are going to solve some problems on differentiability. Let's get it. Consider the first problem. Show that the function f of x defined by x square minus 1 when x is greater than or equal to 1, 1 minus x when x is less than 1 is not differentiable at x equal to 1. First, let us find out the left hand derivative at x equal to 1. Solution. Consider the left hand derivative which is equal to limit of f of x minus f of 1 divided by x minus 1 as x tends to 1 minus, substitute x equal to 1 minus h, I get here limit of f of 1 minus h minus f of 1 whole divided by 1 minus h minus 1 as h tends to 0. If you see here, for x less than 1, the function is defined as 1 minus x. So this will be equal to limit of f of 1 minus h will be equal to 1 minus of 1 minus h minus, by the definition of f of x, f of 1 is equal to 1 minus 1 which is equal to 0. 0 whole divided by minus h as h tends to 0. Okay. Now 1 and 1 gets cancelled, so I get here h. This is equal to limit of h by minus h as h tends to 0 which is equal to minus 1. Now let us find out the right hand derivative RST which is equal to limit of f of x minus f of 1 whole divided by x minus 1 as x tends to 1 plus. To find out this, I substitute x equal to 1 plus h and let limit as h tends to 0. So this will be equal to limit of f of 1 plus h minus f of 1 whole divided by 1 plus h minus 1 as h tends to 0. By the definition of f of x, for any value greater than 1, the function is defined as x square minus 1. So this will be equal to 1 plus h whole square minus 1 minus the value of f of 1 as seen earlier is equal to 0 whole divided by 1 gets cancelled, I get here h as h tends to 0. Now let us expand this. This will be equal to limit of 1 plus h square plus 2h whole divided by h minus 1 as h tends to 0. When I take h as common here, h and h gets cancelled. So limit of h into h plus 2 whole divided by h as h tends to 0, h and h gets cancelled. As h tends to 0, I get here 2. Since left hand derivative equal to minus 1 and right hand derivative equal to 2, the function is not differentiable at x equal to 1. Since LST is not equal to RST, f of x is not differentiable at x equal to 1. There is one more way of doing this problem. If I observe this function on the real line, for the values less than 1, the function is defined as 1 minus x, and for the values greater than or equal to 1, the function is defined as x square minus 1. X square minus 1. When finding the left hand derivative, we are approaching 1 from the left hand side. So the value of f of x is 1 minus x. So this will be equal to limit of 1 minus x minus f of 1 is equal to 0 divided by x minus 1 as x tends to 1. Here I have 1 minus x, take minus 1 common, so x minus 1 and x minus 1 gets cancelled, I get here minus 1. Similarly, when finding right hand derivative, we are approaching 1 from the right hand side, so the function is defined as x square minus 1, so this will be equal to limit of x square minus 1 minus 0 whole divided by x minus 1 as x tends to 1. When I expand this, this will be equal to limit of x minus 1 into x plus 1 whole divided by x minus 1 as x tends to 1. Here x minus 1 and x minus 1 gets cancelled, as x tends to 1, 1 plus 1 will be equal to 2. So since LST not equal to RST, the f of x is not differentiable at x equal to 1. Consider the next problem. Show that the function f of x defined by mod of x minus 1 is differentiable everywhere on the real line except at the point x equal to 1. First, consider f of x equal to mod x minus 1. By the definition of mod x minus 1, this is equal to x minus 1 if x minus 1 is greater than or equal to 0, minus of x minus 1 if x minus 1 is less than 0. In other words, this is equal to x minus 1 if x is greater than or equal to 1, 1 minus x if x is less than 1. Now it is easy to check the differentiability at x equal to 1 and every other point. So let us check the differentiability of this function in 3 different cases. First, I consider a point less than 1 on the real line. Suppose this is 1. I am considering a point less than 1. It will be somewhere here. When finding left hand derivative and right hand derivative at a, we get here f of a minus h and f of a plus h. Choosing h sufficiently small, a minus h and a plus h will be less than 1. Since a minus h is less than 1, we use this definition 1 minus x, so it will be equal to 1 minus of a minus h. Similarly, f of a plus h will be equal to 1 minus of a plus h. So what happens here is 1 minus a and 1 minus a gets cancelled, h by minus h will be equal to minus 1. So we get left hand derivative as minus 1. Similarly, when finding right hand derivative, 1 minus a and 1 minus a gets cancelled, minus h by h gets cancelled, and we get minus 1 again. So at this point, left hand derivative is equal to right hand derivative, therefore the function is differentiable at any point less than 1. Similarly, if we check the differentiability at a point a greater than 1, we get left hand derivative as 1 and right hand derivative as 1. The only difference is for any value a greater than 1, the function is defined as x minus 1. This is the difference. Okay. Since left hand derivative is equal to right hand derivative, the function is clearly differentiable for any value a greater than 1. Finally, we shall check the differentiability at x equal to 1. First, let us find out the left hand derivative, which is equal to limit of f of 1 minus h minus f of 1 divided by 1 minus h minus 1 as h tends to 0. Since 1 minus h is less than 1, the function is defined as 1 minus x. So this will be equal to 1 minus of 1 minus h divided by minus h as h tends to 0. Here 1 and 1 gets cancelled, minus into minus plus, so h by minus h will be equal to minus 1. So I get limit of minus 1 is equal to minus 1. Similarly, if I find out the right hand derivative, here h and h gets cancelled, I get 1. Since left hand derivative is not equal to right hand derivative, the left hand derivative is minus 1, right hand derivative is plus 1. They are not equal, so the function is not differentiable at x equal to 1. By case 1, case 2 and case 3, we have shown that this function is differentiable everywhere on the real line except at the point x equal to 1. Now consider this problem. Check the differentiability of the function f of x equal to 1 plus x when x is less than or equal to 0, equal to x when x is greater than 0 at x equal to 0. If you observe this function is not even continuous at x equal to 0, so it cannot be differentiable at x equal to 0. If you can figure it out by simply looking at the function, then you can use the property of differentiability to show that this function is not differentiable at x equal to 0. We know that if f of x is differentiable at x equal to a, then it is continuous at x equal to e. If I write the contrapositive of this statement, I get if f of x is not continuous at x equal to a, then it is not differentiable at x equal to e. Let us do this. First, let us find out the left hand limit of f of x at x equal to 0. LHL is equal to limit of f of x as x tends to 0 minus. This will be equal to limit of f of 0 minus h as h tends to 0. By the definition, f of 0 minus h will be equal to 1 plus 0 minus h. This is equal to limit of 1 plus 0 minus h as h tends to 0. This will be equal to 1. Again, if I find out the right hand limit, RHL, I get limit of f of x as x tends to 0 plus is equal to limit of f of 0 plus h as h tends to 0. By the definition of f of x, for any value greater than 0, the function is defined as x. So this will be equal to limit of 0 plus h as h tends to 0, which is equal to 0. Since LHL is not equal to RHL, the function is not continuous at x equal to 0. Since LHL not equal to RHL, f of x is not continuous at x equal to 0. So by the property of differentiability, since f of x is not even continuous at x equal to 0, it cannot be differentiable at x equal to 0. So and therefore f of x is not differentiable at x equal to 0. You cannot use this method all the time, because if it is discontinuous at the given point, then it is not differentiable at that point. But if it is continuous at that point, we cannot guarantee that it is not differentiable at that point. So to check the differentiability at a point, first find out the left hand derivative and then find out the right hand derivative. If they are equal, they are differentiable. If they are not equal, it is not differentiable. But if we can intuitively find out the given function is not even continuous at the given point, then you can use this method.